So this next section is about the chi-square test of homogeneity. And if you recall from the previous section, we did another type of chi-square test, the chi-squared goodness of fit, which I'm just going to abbreviate as GOF. So the important thing about the chi-squared goodness of fit was that that one was used when we had one variable and one sample. So then the next type of test that we're going to do is called the chi-square test of homogeneity. And that is going to be used, I'll give you the definition in just a sec, but this one's going to be used when we have one variable. And by the way, for both of these tests, the variable has to be categorical, but there are going to be multiple samples. Okay, so the chi-square test of homogeneity is going to be used to determine if the distribution of a categorical variable is the same for multiple populations. That should be multiple. So the hypotheses for these ones and all chi-square tests, we're going to write in words. And the null hypothesis is going to be that there's no difference in the distribution of the two groups. And the alternative is that there is a difference in the distribution. And something you might notice if you look for everything in this section, all of these problems, is that you are always going to be given a two-way table. So let's go ahead and do an example. Okay, so for example number 1, we want to know if modern technology has changed the distribution of birthdays. So here we have, you don't need to write this down every time, but just because in the previous slide I was saying that it's one variable and multiple samples. So in this case, your variable, which remember is categorical, is going to be the day of the week. So here we also took two samples. Our first sample was the 77 people who were born before 1980. The second sample was the 73 people who were born after 1993. So make sure you know which one is the variable and what the samples are. It sounds like it'd be not that hard, but once you get to the next thing, you're actually going to have to be able to tell which test to use based on this. So go ahead, I want you to maybe try A through C on your own. These have to do with stuff that we did in chapter, I believe it was chapter 1, about conditional distributions with two-way tables and doing graphs of categorical variables. So just try example 1 on your own. So we're actually going to start with example number 2. So before we actually start that example, I'm going to give you two things. The first thing is the formula for the expected counts for two-way tables. This one's a little bit more complicated than the other ones that we've done, the previous one, the goodness of fit. So we're going to be doing row total times column total divided by the overall table total. And then the other thing that we're going to need for this section is our degrees of freedom. The degrees of freedom is going to be the number of rows minus 1 times the number of columns minus 1. Okay, so now what we're going to do is we're going to take the results of the birthday study and we are going to start by calculating the expected counts. So usually when you are asked a question like this, you're just going to do the full hypothesis test. We're going a little bit out of order this time. That's fine. But just know usually you start with the hypotheses, then you do the expected counts. So for these expected counts, I am actually going to fill them into the table. And I'll show you what I mean. Okay, so the way I'm going to do them is each of these cells is going to have its own expected count. Everything that's in this cell right now is an observed count, so that's an important thing to remember. And the other important thing is that when we looked at our counts, you might remember this from the last thing, for this one and the last one, goodness of fit, we are not going to include our totals in our observed counts. So we actually have 7 days and 2 samples, so there's going to be a total of 14 numbers that we fill in. So now I'm going to talk to you about how we are going to find the expected counts. So I did give you a formula for that on the previous slide. If you just want to follow the formula every time, that's totally fine with me. But I'd also like you to understand where things come from. That's very, very important to me that you understand that. Okay, so for example, what we're going to start with is we are going to look at the total amount, for example, for Sunday. And we know that 21 out of 150, which is 14% of people are born on Sunday. So what we expect is that we would expect 14% of each group to be born on Sunday. Okay, so what I mean is that I expect, for example, for the 1993 group, I expect that 14% of 73 are born on a Sunday, which would give me 10.22. So I'm going to put that in there. Now, if this is really confusing to you, like I said, I'm totally fine if you just remember the formula, which, as we got on the previous slide, is going to be the row total, which for the 1993 is 21, times the column total, which for 1993 is 73, over the table total, which is 150. You might notice that the way that this is actually formed in the same way that we just did with the 14%, 21 over 150 times 73. So just know that they are going to give you the same thing. So now I would like you, on your own, using your calculator, to pause the video and fill in the other tables, the table counts on your own, or the expected counts on your own. Just go ahead and fill the rest in, and I'll put them all in, but I want you to try it on your own. Okay, so here's all the values. One thing I want you to kind of eyeball whenever you look at it, whenever you look at the expected versus the observed counts, is see how many of them are close to each other and how many of them are really, really far away. There are a few, like for example, Saturday and Thursday, where they're very, very different from what we expect. So even the Thursday before 1980 was different. So you can kind of eyeball those and just see, like, how are they different? There's a few other examples, like for example, the Monday, that are actually very close to what we expect. So what you're going to find is that maybe some days are the observed is what we expect it to be. Other days, you're going to find that the observed is not what we expect it to be. And that's an important thing to notice when you're looking at chi-squared. So now we're actually going to calculate our chi-squared. So for the chi-squared goodness of fit, you could do it by hand if you wanted. This one you can still do it by hand if you want, but you'll notice that we have 14 cells. So you would be adding together 14 things. It would take a long time. So what I'm going to do, if you recall, here is the formula. It's the sum of your observed minus your expected squared all over the expected. So like, for example, the first one I have, the observed was 12, The expected was 10.75. Then we would do 10.78, I'm sorry. Then we do all that over 10.78. Now, if you want to get full credit on this, you are perfectly allowed to just put the first one, put plus, ... and then finish it from there. And then just do the rest on the calculator. I do not recommend that you do it all by hand. There's a very strong likelihood of making a mistake if you do. So I'm going to review a little bit. We did this in class, but just in case you were absent or you don't remember it. So to find chi-squared on the calculator, you are going to put all of your observed values into L1. You're going to put all of your expected values into L2. So that's the first step. That's the second step. The next thing you're going to do is you are going to do L1 minus L2 squared over L2, and then you're going to store that into list 3. Remember, this is the STO button. It's on your calculator. Then you're going to go to the list menu, which I think might be second stat, I believe. And then you go to math, number 5, which is the sum, and you do sum of L3, and then press enter. So that is going to give you your full chi-squared. I would like you right now to try to do that on your calculator. Hopefully you have your calculator with you. So go ahead and pause and try it. Okay, so if you did that, if you did the chi-squared, you should have gotten 6.554. Okay, so earlier I stated that we were doing this test a little bit out of order because actually we're writing our hypotheses in this next part, but we generally actually will do that first. So my hypothesis, my null hypothesis, is null is always going to be that there's nothing has changed, nothing is different. So in this case, the null hypothesis is that there is no difference in the distributions of older and younger people. And then the alternative hypothesis is just going to be that there is a difference in the distributions of older and younger people. So just a reminder, make sure that when you're writing the hypotheses with the chi-square test, that you do write it in the context of the problem. If you do not, you will lose points. So please make sure to do that. Okay, so second thing is going to be the conditions. And these were both random samples. Make sure that you are clear that they were 2 random samples. They were 2 separate samples. The second thing is going to be the same. Actually, all of these are pretty much the same for all chi-squared tests. The data are counted. And if you want, you can extend that. Expected counts are all at least 5. Or you can just do that one separately. And then our third one is the 10% condition. So because we're looking at 2 separate samples, we're actually going to be looking at the before 1980 and the after 1993 separately. So we know that 77 is less than 10% of all people born before 1980. And then the other one is going to be that 73 is less than 10% of all people born after 1993. Okay, so our final thing is going to be finding the p-value. And before you find the p-value, you do need to mention your degrees of freedom and you need to show how you found them. So the degrees of freedom is going to be the number of rows, minus 1, times the number of columns, minus 1. And just keep in mind that these are not including the totals. So there are going to be 7 rows, which is 7 minus 1. And there are 2 columns. So it's going to actually end up being 6 times 1. So my degrees of freedom is going to be 6. Then we're going to find our p-value. And so I usually like to write the probability that chi-squared is greater than 6.55. If you want, you can write the calculator stuff, but writing the probability that chi-squared is greater is probably much better. You would use on your calculator chi-squared CDF, 6.55, any big number is fine, and then 6 is equal to 0.364. So it's a pretty high p-value. The other thing that you might want to do is drawing a chi-squared curve is not going to hurt. So it'll look kind of like this. And then you're going to put in your 6.55 here. If you want to find a better curve, actually on your calculator, when you run chi-squared CDF, you can press draw and you'll find a good picture of it that it's probably going to look better and more accurate than this. I'm just kind of guessing here, so it's probably not going to be perfect. So anyway, let's go back to the p-value. This is a really high p-value. So because the p-value is high, I'm going to fail to reject the null hypothesis. And it is a good idea if you like put alpha equals 0.05 somewhere. That's always a nice idea. So what we're going to say is that there is no evidence of whatever our alternative hypothesis. And I just looked and I realized I wrote my alternative as HO, but it should be an HA. So there is no evidence that there's a difference in the distributions of older and younger people.